Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is crosstalk in 6-layer PCBs. How does it sneakily occur in 6-layer boards? In high-speed PCB design, signal integrity is always a key focus for us. One of the most common hidden killers is crosstalk. In 4-layer boards, we've discussed crosstalk within the same layer, but in more complex 6-layer boards, how does it sneakily occur? Today, let's dive deeper. Let's analyze the crosstalk mechanism in 6-layer boards. Let's still use this PCB as an example. What exactly are the dangers of crosstalk and how serious can it be? So what is the definition of crosstalk? Simply put, when a signal undergoes a change in voltage due to electromagnetic coupling, it can induce unwanted voltage or current on a nearby line. It's like two people whispering to each other, but accidentally being overheard by someone nearby. Do you remember the diagram of the materials we showed when discussing 4-layer boards? In that diagram, one line is the aggressor line. Through capacitive or inductive coupling, the signal is transmitted to the victim line. So what are the dangers of crosstalk? First, there's signal distortion. The noise from the aggressor will be superimposed onto the normal signal of the signal line. This can lead to severe distortion, resulting in phenomena like overshoot and undershoot. This is easy to understand. Originally, there is a normal signal on the victim line, but when the signal from the aggressor line couples over, it becomes dangerous. The normal signal on the victim line gets superimposed with the coupled signal. This causes signal distortion. Secondly, it can cause false triggering. Severe crosstalk may cause the voltage on the victim line to exceed or fall below certain thresholds. A logic threshold may cause the receiver to misinterpret the signal, leading to system malfunctions or data errors. This is also the case, especially when the victim signal is relatively weak. The induced signal becomes comparatively large, which can easily cause problems. Finally, it can lead to system instability. The accumulated interference will reduce the overall reliability and stability of the system. How does crosstalk penetrate between adjacent layers in a 6-layer board? In a 6-layer board, crosstalk not only occurs within the same layer, but more importantly, between adjacent layers. Let's take the recommended stack-up strategy as an example. Signal end signal, power CND signal. As an example to see how it is generated, let's first look at this internal structure. That is, we recommended several top-layer signal TNT signals. Power, click on the quotation marks. This kind of plane before and after. What is the specific mechanism by which crosstalk is generated? First, it is through capacitive coupling. Even if there is a plain layer, such as ground or power, serving as isolation, the electromagnetic field will still pass through the dielectric layer between them on the aggressor line. When the electric field or magnetic field changes, part of the energy is leaked to the adjacent layer. A new second layer induces noise. Let's talk about this. For example, between L1 and L3, even though there is TNT as isolation, if the signal on L1 is too strong, part of the signal will still penetrate the L ground layer and cause interference. Next is edge coupling. When the signal is near the edge of the plane layer, or when the plane layer is split, the electromagnetic field is more likely to spread to the adjacent layer. The breadbox analogy is also easy to understand. Let's look at it on the map again. Thank you for clicking on it. Suppose this is a signal line. When it's at the edge, although the downward part of its magnetic field will be reasonably neutralized by the ground, the outward part has no shielding or isolation at all. It will then escape from the edge of the board and enter other layers, interfering with them. This is edge coupling, which then causes interference. When a signal passes through a via for layer switching, the via itself can also generate electromagnetic fields, and this may cause diffusion to the surrounding signal layers. It increases. This different kind of interference affects us when, as we discussed in the 4-layer board session, if we drill holes on these signal lines. For strong signals or critical signals, it's required to add a ring around the via. Add another ring. Adding another ring acts as shielding during the D process, which is to prevent this kind of interference caused by the via. Next is the return path, if the signal's return path is not ideal. For example, if the return path needs to detour or the return path's plane is discontinuous. The resulting electromagnetic field will cover a larger area and is more likely to couple to adjacent layers. Therefore, it's important to keep it as close as possible so that all return currents flow back properly. For signals like these, vias are placed nearby. Why do we strongly recommend this particular method? The innovative stacking method significantly helps to effectively suppress unwanted crosstalk. Let us now carefully examine this detailed stack-up structure for a much clearer and more comprehensive understanding of its benefits and operational principles. First, the plane layer primarily serves as an effective isolation. In this docking structure, each signal is closely paired with a reference plane, either ground or power. These shielding planes act like screen walls, able to absorb and confine electromagnetic fields from signal lines, thereby greatly reducing the energy leakage between adjacent signal layers. So as we can see, layer 1 is close to L2, L3 is close to L4, and L3 is sandwiched between L2 and L4. L6 is close to L5. Each layer has a dedicated reference plane as its ground plane. Next, there are multiple layers of isolation. Compared to a 4-layer board, a 6-layer board provides more plane layers. For example, layer 2 acts as an intermediate isolation for layer 1. L3 is equivalent to layer 2. The ground and power planes are sandwiched in between. The signals on the bottom layer are isolated by the gap of layer 5. This kind of multi-layer isolation allows for better control of the plane. Today we reviewed the definition and hazards of crosstalk, gained an in-depth understanding of crosstalk between adjacent signal layers in 6-layer boards and its generation mechanism. We also looked at recommended 6-layer board stack-ups, especially how to suppress crosstalk through the proper use of plane layers. However, relying solely on stack-up is not enough. In the next lesson, we will delve into how to make adjustments during actual routing. We will further tame hidden crosstalk by strategies such as adjusting line spacing and using guard traces to ensure a better signal transmission environment. If you enjoyed this video, please subscribe to my channel for more content. Thank you all.